All right, everyone, quiet down, quiet down. Rowdy bunch here this morning. Wow, this mic is loud. Okay, so don't be too close to the mic. All right, so welcome everybody. Welcome. My name is Matt Ruark. I serve on the Madison Steering Committee for the Dairy Innovation Hub. This is a session on land and water stewardship. I will be serving as the chair of the steering committee this upcoming year. I'm a professor in the Department of Soil Science and do a lot of research in this area of land and water stewardship around dairy production systems. So for those that are unfamiliar with the Dairy Innovation Hub, UW-Madison has a steering committee. What do we do on that steering committee? We help administer different grants. We fund research in short-term high impact research, postdoc grants, equipment grants, and everyone's favorite graduate student grants. So a lot of the research that we've supported over the past few years, you can check out, well, obviously at events like this. Also, make sure you go check out the poster session. Today, I'm joined by my colleague, Margaret Kalsick, and together we'll be moderating today's session.
Thanks, Matt. Like Matt, I serve on the Madison Steering Committee of the Dairy Innovation Hub, and I'm also an associate professor in the Department of Biological Systems Engineering here at UW-Madison. My position is funded by the Dairy Innovation Hub, so I'm one of those faculty. We have roughly 2 hours together, and each hour will be structured a little bit differently. The first hour will showcase 3 individual projects involving land and water stewardship and dairy systems. Our second hour will present a big picture idea of dairy farm sustainability, broken into 3 different areas. The length of our speakers will vary slightly, but in each hour you will have time for questions and you will and hear any further comments that they have. We want this to be an open discussion and a place to share ideas and make connections for collaborations. Remember, we are recording the session today, so it's important that we use the mics for questions or repeat the question on the mic. With that, I'm pleased to introduce our first speaker. Joe Sanford is an assistant professor in the School of Agriculture at UW-Platteville. His position is funded by the Dairy Innovation Hub, and his research interest is in agriculture wastewater management, including farmstead and edge of field runoff, nutrient management, and precision manure application, to name a few. Welcome, Joe.
Yeah.
I'm gonna stick with this mic.
All right. I'm going to stick here. I'll try not to move around. All right. Thank you for that introduction. Yeah, I'm Joe Sanford. I'm a faculty member at UW-Platteville through the Dairy Innovation Hub. I'm in the Soil and Crop Science department, but I'm actually an agriculture engineer by training. And today what I want to talk to you all about a little bit is talk about biochar and ways that we can possibly incorporate biochar into dairy waste management systems. And so I'm going to start off my presentation. I'm the first one, so I get to just kind of talk about manure a little bit. That's the nice thing about going first. Manure and dairy, they go together. And in Wisconsin, we produce a lot of manure. So every year, around 35 megatons of manure is produced. And that manure has to go somewhere. The benefit, one thing I like to talk about with manure is, it gets a bad name a lot of the time. But it is really important in terms of on-farm sustainability. We need to grow crops for our livestock. Those crops need nutrients, and so that manure, has those essential nutrients in them that we can use to offset the use of synthetic fertilizers, and that has its own environmental benefits. But there are several environmental concerns associated with manure as well. In Wisconsin, one major issue is going to be legacy phosphorus. I'm not going to get into this too much because I know we're having another talk on this, and I think the next talk is on this, so I won't get into that too much. But legacy phosphorus is a big issue where we have the overapplication of phosphorus and saturation. We also have concerns with leaching of nutrients, runoff of nutrients as well, that can impact agroecosystems. And then also emissions, which is often not looked at quite as closely as some of the water quality things, but in terms of emissions as well, dairy systems do result in quite a bit of emissions of greenhouse gases, methane, nitrous oxide, and also ammonium as well. And so what I'm going to talk about is my kind of grand scheme to add biochar and to solve all the world's problems here with dairy industry. Before we get into that too much, though, just a little talk about what biochar is. So biochar is a product of a process called pyrolysis. So we're taking a biomass, we're heating it up at very high temperatures under oxygen limiting conditions. And we are producing 3 different products. We're producing a syngas, a bio oil. Both of these can be used for energy production. And then biochar, which is a byproduct of the process that kind of looks like a charcoal, kind of similar properties to activated carbon. And because of its properties, it's gotten a lot of interest in a lot of different uses. So it has a very high carbon content. So depending on what you make the biochar out of, somewhere between 50 to 80% or higher carbon content of that biochar. It also has a very high surface area, has some cation exchange capacity as well, which makes it interesting for nutrient retention and bonding. And then it has an alkaline pH as well. And so biochar has gotten a lot of attention in the last few years for land application. And so there's been a lot of studies, and I'm not going to go into all the details, but biochar has been shown to improve nutrient retention, particularly help mitigate or reduce nitrate leaching from agricultural systems. In sandier soils, it's been shown to improve water use efficiency in irrigation systems. In soils where you have a lot of clay, it's been shown to improve aeration. But the big one that it's gotten a lot of attention for is due to its carbon sequestration potential. And so biochar, when incorporated into the soil, can last anywhere from hundreds to thousands of years in the soil. And in terms of climate, greenhouse gases, carbon sequestration, it's been found to be one of the more promising methods potentially to sequester some carbon. And in agricultural settings where we typically see a decrease in soil carbon, decrease in organic matter, that shows an opportunity where we can potentially incorporate that in to bring that carbon and organic matter back up. This has been a little bit further accelerated in recent years due to the NRCS 336 code that just came out. Wisconsin is in the process of adopting this, but it's essentially a conservation practice standard for applying biochar to agricultural fields. And with this is going to come some cost sharing for farmers as well. And so in the next few years, I think we're going to see a lot more biochar application occurring. And so getting into my grand plans here, applying biochar to the landscape has its benefits, but I think there's a lot of other opportunities for incorporating biochar into the farm before it gets onto the landscape. So what we're going to talk about today a little bit, things that my research group has been working on, has been looking at how biochar applications influence particularly emissions after land application of manure. We've also been looking at incorporating biochar into manure storages, both solid and liquid, and that's impact on emissions, nutrient retention. We've also looked at incorporating into anaerobic digestion systems, and we've also been looking at making biochar out of manure as a fertilizer source. And so what we're going to focus on the next few minutes is going to be manure storage and anaerobic digestion systems, because that's the most advanced research. And then I might have a little bit of time to chat about a couple of the ongoing things. But manure storages. So manure storages are very essential in our livestock production, particularly here in Wisconsin. It has its benefits to allow us to apply manure at the proper times of the year, but there are some concerns associated with manure storages, particularly around emissions. So in terms of emissions, manure storages are a fairly significant source of methane emissions. So during storage, we have anaerobic conditions, which is going to lead to some methane emissions. We also have fairly high ammonia emissions as well during storage as well, and is also a source of odor. And so in the last few years, there's been a lot of changes in manure processing systems, and we've seen kind of manure storage is looking like this with this nice crust over the top to looking more like a swimming pool. And when it looks more like a swimming pool due to all the water that we're adding into the system, this is where we run into some issues with ammonia particularly and methane, where there's no natural crust to kind of prevent some of those emissions from coming off. And so one thing that my lab group's been looking at is incorporating biochar over the surface of this manure storage. as a permeable cover to help offset some of these emissions potentially. This is currently done with other biomass, but that biomass generally has a very high biodegradation, and so doesn't stay on the surface very long. So what we've been doing is we've been doing a pilot study. This is a Dairy Innovation Hub funded project where we're looking at the impacts of these storage covers. And so what we did in 5-gallon buckets, we filled them up with manure. And then we put 2-inch covers over the top of these manure storages. And what we looked at was kind of the raw biomass that might typically be used, and then biomass that had been converted into biochar. And so we did this with a few different products. We looked at wood chips. We looked at manure solids, corn stover, straw, and we produced biochar at a few different temperatures as well. And then we took regular measurements using our FTIR sensor to get emissions of some of the greenhouse gases and also ammonia off the surface of that storage. And so from that study, we got some very promising results in terms of ammonia reduction. And so for ammonia reduction here, this gray bar is our control buckets. So this had no cover on the top of it. And then all these other bars are from our treatments. And what we can see here is for wood biochar, so that wood chip, it was very effective at reducing ammonia emissions, particularly compared to that raw material as well, and also the control. And so we almost, we had a huge reduction in ammonia emissions from our wood chip biochar application over the top of the surface. For some of our other biomasses, so we applied raw manure solids that had been dried over the top. We applied corn stover as well, and also their biochar companions. And what we found was a little bit of interesting results. There's a lot of variability in some of our biochars, particularly. And so they were not as effective as their raw companions, but they still in general reduce that ammonia emissions off the surface. And so in terms of biochar, incorporating biochar into the system to sequester some of that carbon, using biochar as a manure cover is very promising for reducing some of those ammonia emissions off of that manure storage. In terms of greenhouse gases, the goal of this study was to address that ammonia and hopefully not increase greenhouse gas emissions. And what we found here was that for most of our biochars, most of our covers that we applied to the surface, really no impact in terms of greenhouse gas emissions. However, our wood chip biochar, particularly our lower temperature, did actually increase greenhouse gas emissions a little bit. And so this is a little bit of an interesting situation where we had this increase in greenhouse gas emissions. And what we found was the reason for this was this bump in greenhouse gas emissions, particularly from this treatment here, was due to nitrous oxide emissions off the surface of that storage, which we believe has to do something with the surface and the particle size of the biochar, creating some anoxic conditions right at the surface that promote denitrification and incomplete denitrification to nitrous oxide. And so one thing that we're going to be looking at now in our next set of studies is looking at particle size, seeing if we can reduce that particle size. So these are very large particles compared to a lot of our other materials. If we decrease the particle size, will we still have that decrease in ammonia emissions, but also not impact those greenhouse gas emissions? The other study we've been working on as well is anaerobic digestion systems. So we've been looking at in anaerobic digestion systems. I think everyone in here is probably fairly familiar with it, but it's renewable gas or renewable energy process where we're taking manure, generally creating biogas, a digestate, a lot of different benefits on both sides of those things. But one major issue with biogas, in particularly dairy systems, is hydrogen sulfide production. So hydrogen sulfide is highly corrosive and we have to remove it. And we spend a lot of our operating budget at anaerobic digestion systems removing that hydrogen sulfide. And so one thing we wanted to look at was, can we use biochar to reduce that hydrogen sulfide from starting in the first place? And so what we've been doing in our lab group has been looking at some batch systems, assessing the impacts of dosing biochar directly into the digester. So we're taking biochar, dosing it in there, mixing it in with that manure, and looking at the biogas production in terms of biogas quality, quantity, and also that hydrogen sulfide. For hydrogen sulfide, what we found in this study is that biochar is fairly significant at reducing hydrogen sulfide production if the temperature is low. So temperature is a pretty major factor here. And so this is an example from one study we did. So we looked at a lot of different biomasses, produced the material at a lot of different temperatures. And so generally what we've found through all of our, and this trend is hold true, is that low temperature biochars, particularly those below 425 degrees Celsius, are very effective at reducing hydrogen sulfide production in our anaerobic digestion system. As the temperature increases, we generally see a decline in the ability of that biochar to reduce that hydrogen sulfide. And so temperature is a major factor here in terms of biochar's ability to reduce hydrogen sulfide production. In addition, feedstock doesn't seem to really matter. So in terms of feedstock, we looked at a lot of different feedstocks. And so this was from one study comparing all of our different feedstocks. So we looked at aspen wood, pine, corn stover, and manure solids. And we looked at the same temperature and put them head to head. And what we found was that temperature or the feedstock really didn't matter. They were all significantly similar in terms of their H2S reduction. And so what we found here is that we can reduce hydrogen sulfide production in the digester by dosing it in. And that the material that we produce that biochar from is not that much of importance. However, the temperature is very critical. From the biogas side of things, so in terms of renewable energy, how much biogas to produce, the quality of it's very important. And so a couple of things that we looked at here was both the biogas quantity. And so what we found in terms of biogas production down here, so this is from that pine shavings study, really no impact to the biogas quantity that was significant. And so this, and so really no impact. So it didn't increase or decrease that biogas production. In terms of methane potential, which is important for that energy production. Again, very similar concentrations across the study period. And this held true for all of our studies looking at all the different biomasses. And so you might be thinking, well, that's kind of a bummer. You didn't increase biogas production. But in terms of RIN credits, which renewable energy or digesters can get to help fund some of these projects, that's actually a good thing because you can't add any additional material into those digesters that will increase biogas production. And so this is kind of showing what we've found so far is that and really there's not much biomethane potential in that biochar that we've added into the system. So our kind of next steps here, what we're going to be looking at is we've only looked at one dosing rate. So we're going to be adding in some different doses of biochar into the system to see how that might impact the system. And then also looking at everything we've done so far has been on a batch study scale. And so we're going to be looking at some continuous systems in the lab and also in the field to see how it kind of correlates to those larger systems that are more representative of what we see on farm. So my last few minutes here, we're just going to talk briefly about some of our current studies that are in the field. I just kind of wanted to put a plug in for what we're doing right now on some of these things. And so as I mentioned at the beginning of the talk, legacy phosphorus is a big issue. And one of the ways to deal with legacy phosphorus in dairy systems is to move phosphorus out of the watershed, which is very difficult when a lot of our phosphorus is in that manure. And so one thing we've been looking at our lab is actually taking that manure solid and converting it into biochar. And what we found in some of our laboratory scale work that we've done is that by going through this process, we have a huge densification of phosphorus. And so we have a very dense product. And so instead of a wet manure solid that is maybe somewhere around 5 pounds per ton, we can create a biochar that's somewhere around 30 to 35 pounds of phosphorus per ton of material, right? So densifying that down, very lightweight product that we can now move farther from the away from the farm. And in terms of the available phosphorus, we did some incubation studies that found really wasn't much difference comparing the wet manure solids to the dry or to the biochar. And so what we're currently doing right now up at Arlington is we're doing a study looking at in the field how we can use manure-derived biochar as a fertilizer source for corn silage production. So that's one study that we currently got going on. They're out in the field right now actually applying the biochar. I guess I'm lucky to be here. Another thing that we were looking at that I mentioned before was that impact of biochar on manure application. So we know during manure application, there are quite a bit of losses of ammonia. Generally, right after application, we have losses of nitrous oxide as well. And so one thing that we want to look at is how, with this 336 standard coming out, how biochar is going to influence those emissions at different rates. And so what's the benefit of different biochar application rates? What's the benefit of different biochar types? And so one thing we're doing right now is in Arlington as well, we're setting up a study where we're looking at comparing just regular manure application in a corn silage system and looking at different rates of biochar, different rates of biochar produced from different products such as wood and manure solids, and then also comparing some of these different feedstocks as well. And so what we're going to be doing is in this study, taking greenhouse gas measurements on a regular basis to look at impacts of ammonia and nitrous oxide. We're going to be taking soil samples to look at nutrient retention and things like that in this study. And so with that, I ended on time. All right, perfect. I just want to say thank you. I'm just going to put in a shameless plug for myself here. This research has been funded by the Dairy Innovation Hub to start with, but myself and a few others recently got a big, or not a huge, but a USDA and LGCA project where we were able to purchase a pyrolysis unit up at Pioneer Farm. And so this is what's producing a lot of the biochar for our current work, and we're looking for future collaborations using this unit. So if anyone has some biochar ideas, come talk to me. Well, thank you.
Is this on? Okay. We're a little short on time, but we have time for one question. So is there a burning question in the room?
Thank you, Matt. I was interested in the reduction of methane from the lagoon storage. So is the biochar serving simply as a floating barrier on top to make diffusion of methane more difficult, or is it absorbing the methane that would otherwise have been released into the atmosphere?
Yeah, so in our study right now, we actually didn't see a reduction in methane. So it was there may be some small reductions, but if you looked at the significance, they're not statistically different, really. We haven't seen any huge reductions in methane. In terms of the ammonia side of things, it's a little bit of both. So that floating cover for ammonia is keeping it kind of trapping it in. Biochar also has a very high affinity for ammonium and ammonia absorption. And so we did see an increase in that ammonia concentration on the biochar after the study, where it did soak up some of that ammonia that could have potentially been lost. So it's a little bit of both. All right.
That's all. Thanks. Thank you all again. All right, our next speaker is Joseph Andrews. He is an assistant professor of mechanical engineering and electrical and computer engineering here at UW-Madison. He leads the laboratory for printed electronics and sensors. And the focus of that laboratory is developing new printed electronic devices for interdisciplinary sensing applications that you'll hear about today. So with that, help me welcome our speaker.
Thanks for the introduction, Matt. And I also want to point out this presentation was developed with Professor Jingyi Huang from the Soil Science Department. He's been a partner in this work and has really made it what it is. Over in engineering, we're really good at making shiny hammers, and we go around looking for nails. So we'll come up with a solution whether you have a problem or not. And so working directly with Jingyi in the Soil Science Department has made sure that we can keep the work focused on benefiting agricultural applications. This is the talk outline. I'll talk, just by explaining what printed electronics is in general and why it can be beneficial for use in soil sensing applications. I'll talk about our ongoing research in developing these sensors, and then also kind of what's next in terms of using these sensors for looking at nutrient cycles in agricultural applications. So those of you who are not familiar with printed electronics, it's very similar to 3D printing. So it's an additive manufacturing method of developing electronic devices. I have a couple videos here where you can see we're depositing thin films of conductors. We can also deposit insulators as well as semiconductors to form fully functional devices. So we can make large arrays of electronics. We can print on a wide variety of substrates. So we can print on flexible substrates, stretchable substrates, or low temperature substrates for different applications. And I also have a nice video of printing Bucky Badger just to show that we can print complex geometries and complex shapes. So these are all what we would call direct write printing, where we upload a digital pattern and then we can print it right away. There's also template methods such as these in the bottom left, roll-to-roll printing, as well as screen printing. And really the benefits for these are large area integration, freedom and substrate choice. Like I said, printing on things that are flexible or stretchable, and you have lower energy and material cost in fabricating these electronic devices. I want to focus in on large area integration in particular. There's a couple applications where this matters. So one thing that we work on in our lab is display technology. I'm not talking about that today. Instead, I'm going to talk about large area distributed sensing. And so when I say large area, I'm really talking about something that's larger than a typical silicon wafer. So if we want to, sense something that's on the order of feet or on the order of meters, printed electronics is a really good method for fabricating these type of devices. And so we can look at distributed sensors for wearable electronics. And then in the bottom right, I'm talking here about distributed chemical sensors for soil nutrient management. And so soil, as everybody is aware, is a heterogeneous environment. So you don't want to sense just a very small piece of the soil. We want something that's large area so that we can sense the population of the soil. And we also want something that's distributed so we can tell how things are moving, both in terms of depth and then lateral spatial resolution as well. And in particular, we're looking at nutrient leaching. So we've developed these soil sensors particularly to look at nitrate leaching. And so this plot is a little bit small on this screen here, but this is just showing a typical cycle of everything that kind of goes onto the soil to make crops. And then what we're interested in avoiding and ultimately in measuring is this leaching loss. So as you apply artificial fertilizer or manure, and then there's rain events, you can end up losing those nutrients through the bottom of the soil into the water basin. And in particular, we're interested in nitrate leaching. Nitrate leaching is a big problem here in Wisconsin. It causes adverse health effects in drinking water. This is actually, and I'll read it for those of you that are in the back. This is a notice that I saw when I was camping in western Wisconsin, and notice the nitrate concentrations in this campsite water are higher than is advisable by the health department. It affects babies and pregnant women. Both my wife and sister were pregnant, so I quickly got in the car and went to a quick trip to get some gallon spring water for our camping trip. But it is a big problem here in the state of Wisconsin. Also, other nutrient losses such as phosphate can lead to these algae blooms that we're all familiar with seeing in the summer. And so ultimately our goal is to be able to measure these nutrient losses so that we can look at best management practices in real time and how they're helping the situation. Okay, so that's a little bit of a long preamble. So now I'll go through the technology a little bit quickly. Our goal here was to develop a multi-sensor system. So we want to be able to measure soil moisture as well as soil nitrate. And so here is kind of, our back of the box design. We were actually fortunate enough to get a short-term high impact grant from the Dairy Hub. And so that really kicked off the work. This was our initial design, and this is kind of the final product where we are now. We need to be able to measure both moisture, as you can see on this left-hand side, as well as nitrate so that we can see how the nitrate is moving throughout the soil and really give you the same kind of effect as a lysimeter. We also want to measure temperature because that plays a role in the calibration of our sensors. I'm going to skip through the moisture measurements. We use basically a technique called coplanar capacitors, where we have an electric field that extends out of plane, and we use that to quantify the permittivity of the soil, which is directly correlated with the moisture. And so you can see we have a linear relationship. These are 5 different sensors where we're optimizing the geometry. And if we use the widest electrodes, we get a really nice sensitivity to volumetric moisture content from about 5% all the way up to full saturation of about 30%. And again, let me skip through. So moisture, we're able to detect using this capacitive technique. I want to spend a little bit more time talking about the nitrate. So here's a schematic of our nitrate sensor. So we're using something called open circuit potentiometry, where we have a working electrode and a reference electrode. On top of the working electrode, we have an ion selective film that only allows nitrate ions to diffuse through and absorb onto our working electrode. Our reference electrode, we have a Nafion film, which prevents anion diffusion. And so when there is the presence of nitrate that is mobile, that means diffuse or dissolve nitrate in moisture, we can get an electric potential difference between the working electrode and the reference electrode. And here you can see this is our sensor operating in a liquid solution. And we hit a sensitivity of about minus 58 millivolts per decade, which is the fundamental limit for these type of sensors as identified by the Nernst equation up top. So we're able to use these sensors in liquid media, but that's not the innovative piece of our design. What we really want is a sensor that can work in soil. And so to work in soil, we kind of had to step back and think, okay, how are we going to get this sensor that works really well in liquid solutions to work in soil? We thought about different design ideas of maybe having like a pump that pumps in, extracts water from the soil. It's like, well, that's a little bit cumbersome. Ultimately, what we landed on is using a wicking-like membrane. So we can use a nanoporous polymer membrane that has some hydrophilicity to absorb the moisture from the soil. We try to have a similar water potential as soil. So soil, as everybody knows, can kind of act like a sponge and pull water in. We want our membrane to do the same thing. And so this is a material called PVDF. It's a polymer membrane that's nanoporous. And so it prevents soil particles from diffusing to our sensor, but it enables nitrate-laden solution to diffuse to the sensor. And so this polymer membrane almost looks like a paper, and we can just adhere it directly onto our printed electrodes. And now we're able to sense, this is still in liquid. We wanted to make sure it works the same in liquid as it does without the film, and it does. So we get about the same sensitivity, 58.6 millivolts per decade. And now we wanted to see, okay, does it work in soil? So here on the left is the sensor without PVDF in soil, and you can see that the sensor actually never saturates, and this is because the negatively charged soil particles screen out the nitrate effects and we're not able to sense it. With the PVDF, however, because of that nanoporosity, we're able to get saturated signals at various levels of nitrate due to kind of making sure that we're not sensing the charged soil particles. And we were able to demonstrate this in all kinds of different soils, so both sand, silt, loam. We're able to see that it performs the same as it does in aqueous solution. So we took a sensor, worked really well in aqueous solution, and now we made it so that it works really well in soil. And that's because of that passivation technique that I talked about previously, where it facilitates this nitrate-laden infiltration to the sensor surface, and it prevents the absorption of these charged soil particles. A couple more details about our sensor. So here's the recoverability. So we can do multiple cycles in silt, loam, and sand. So this is going from 50 ppm of nitrate all the way up to 500 ppm and back and forth. We wanted to prove that, okay, we can recover the sensor even after really high concentrations of nitrate, as well as specificity. So we were a little bit worried that we would, be cross-sensitive to other ions in soil. And we looked at a few different chlorine particles as well as phosphate, and the cross sensitivity is really quite low because of that ion selective membrane. And so now we're working on integrating these sensors all together into a multi-sensor platform. So we have our nitrate sensor, our moisture sensor, and a digital temperature sensor as well. And so there's a poster downstairs if you want to learn a little bit more about these what we call sensing stickers. And so we have all of this integrated onto a flexible substrate, which can then adhere onto a rod, and we can bury that rod and measure nitrate and moisture at different locations. Our first prototypes have these sensing stickers at 10 centimeters, 20 centimeters, 30 centimeters, 50 centimeters, all the way up to 1 meter. And so that we can measure how that nitrate is moving throughout the soil and really get the same kind of data that you would from a lysimeter, but from a much simpler, lower cost and easier to install probe. And so as we think about what's next, so this summer we're doing some big tests. We're basically taking these sensors and comparing them with lysimeters that have been installed at Arlington Research Station. And so this is a silt loam type soil. This was a slide Jingyi provided for me, so I'm not going to provide too many comments on this slide, but to say that we're ready to start burying the sensors, and we will in the next week or so. And so stay tuned for that data comparing our lower cost printed electronic sensors to these already installed lysimeters. Then we're also doing some nitrate leaching studies at Hancock. We're burying these in potato fields, actually, that are undergoing different nitrate applications or different management practices, so that we can observe how the nitrate leaching is affected by these different practices. We actually had a chance to bury one of the sensing probes last summer, and it worked for about 2 weeks, and then we had some waterproofing issues. So we've gone back to the drawing board and really made these sensors much more robust. And so we're pretty confident in this next round. The last thing I wanted to point out is a newly established collaboration with Professor Jill Coleman-Wasik at UW River Falls, where we're going to install these sensors directly into wells. So we'll look at nitrate in well waters, and we can look at real-time nitrate changes within these wells. We're a little bit worried about putting these printed silver nanoparticle thin films in people's drinking water. So we'll pump the water away from the well, sense it, and then dispose of it. But ultimately, these sensors will allow us to get real-time information regarding the nitrate levels within drinking water wells, particularly in Northwest Wisconsin is where we'll be looking at. And so with that is a little bit of a quick run through of our technology. Again, we have a poster downstairs that Kwan Yu Chen, one of the students that's been leading the work, will present. So if you're interested in learning more, you can meet him down there. We can even bring a couple of our sensor prototypes if you want to look at those as well. So thanks to all our collaborators. So we have some collaborators that we're working with in the future of getting these sensors out there, including Matt and Xia. And again, Jill, we're working with to sense this well water in the near future as well. We want to thank the funding agencies. Again, the Dairy Innovation Hub was really our Kickstarter to getting into this field, and now we have a USDA and an NSF project that's continuing to fund the work as we move forward. So thank you so much for your attention. Hopefully I saved enough time for a question or two, and hope to see you down at the poster session for more in-depth conversations.
We have time for one question up front here.
Thanks. Yeah, two very brief points. Has it been determined that dairying is the origin of the nitrate and nitrite pollutions at this state park? You mentioned also, what does NatCion stand for? I assume it's a combination of two or more words.
The first question was, what is the contributing factor to the nitrate that's contaminating the well water? I think at this point it's, and forgive me if I'm using the terminology wrong, but it's a non-point source
Right.
pollutant where, it's not exactly determined where it's coming from. And so that's something that we're interested in looking at is how agricultural practices can be used to perhaps reduce this. So that's something that we're interested in using this sensor as somewhat of a surveillance tool to see in real time, what's leading to these fluxes in nitrate within the well water. And I think your second question was about Nafion, which was one of the thin film layers that we're using. Is that?
Right.
So Nafion, I believe it's the trade name for the material. So it's a commercial material that you can buy. So it's some kind of polymer membrane. I think Nafion is the trade name for it. So it's a proton exchange membrane that's used in a lot of applications.
Okay, so it doesn't have anything to do with sodium ions or anything like that?
I don't believe so. I would need to look at the chemical makeup, but I think it's just some marketing name that whatever company came up with.
Well, thank you so much, Joe.
Thank you.
All right, our next speaker, come on up, Alfred. So I'm pleased to announce our last speaker in this hour is Alfred Hartemink. And Alfred is a professor of soil science at UW-Madison. His research interests include soil mapping and soil information, digital soil mapping, soil carbon, tropical soils and tropical agriculture, soil fertility and global soil science, as well as soil publications and soil science history. Please welcome Alfred.
Thank you very much. I will say on forehand, I do not have too much of results yet. This is work in progress. In fact, it has not even started so much, but I thought I'll bounce it off to you just to perhaps get some ideas going and some discussion on the direction that we're taking and whether you think it makes sense. So I'll run through it. We currently are mapping the soils of Marshfield Agricultural Station at a very dense resolution, and Dr. Gafo Gosukara and myself are doing most of that work, largely focusing on soil carbon and whether we can map that in detail in these glossudals, these alpha soils with glossic horizons. I'll come back to that later, and the work is done with Eric Young of ARS, and the phosphorus work will be done with Laura Ward-Good. Many of you might know her. So I will say a bit about phosphorus in Wisconsin, just as most of us have this introductory slide. So the average soil p-test is over 50 milligrams per kilogram. As we know, in many places, it's even higher, up to 100. We know that corn or maize removes about 3 to 5 milligrams of milligram of P per kilogram of soil per year. We know that the manure applications is often determined by nitrogen and not by the phosphorus rate, so to speak, or by the phosphorus removal, I should say. And that 30% of the fertilizer and feed phosphorus exported in crops and animal products means the remaining 70% is not, bless you. So 2/3 of the phosphorus is lost through surface losses. That also means that 1/3 of the phosphorus is not lost through surface losses. So I think this is the work of Dr. Ruark and the Discovery Farms that shows, maybe the light can go off or not. I can barely see it myself. Is that possible? Greg, a miracle. Such a small finger. Look at it. Thank you. So here we see the difference between dissolved phosphorus and particular phosphorus. You see that much of that is running off in the spring and later on when the rains are intense. That's some of the great work of the Discovery Farm that prompted some of these ideas. So we will focus to some extent on phosphorus saturation, and is a very difficult complex that has been simplified perhaps a little bit too much. So it's the ratio between the amount of P present, and that's already a questionable amount, and the total capacity of the soil to retain the phosphorus. And that is to be determined often as the ratio of soil phosphorus over the amount of aluminium or aluminum and iron, something like that. And that has been perceived to be pH dependent, which is somewhat schematic and possibly not true in every condition, as we figured out. So if the soil is to be saturated with phosphorus, if that were to happen, then the idea is that soluble phosphorus is lost, either by surface runoff, because it's not held onto, or by leaching. And that particular is, of course, dangerous if you have shallow groundwaters. And then, of course, some of the phosphorus being lost by eroding soil particles. We will question this idea of this aluminium and phosphorus binding of in relationship to the total phosphorus at different pHs. That is much dependent on a lot of other factors, in particular the mineralogy and the carbon content. So we know that Wisconsin, of course, is particularly blessed with this notion of the phosphorus index, and that's been estimated. It's been long time used. Many fields have this phosphorus index. It's a very useful thing. It also shows that much of the phosphorus loss comes from a very small area Hence our focus on the hotspots rather than the entire fields. As it says here, that 80% of the loss comes from about 20% of the watershed. So the question is, where are those 20%, and can we quickly identify it, and then perhaps can we remediate it, perhaps with the biochar of some of the other technologies that were mentioned in the previous talks. So not a lot of work has been done, unless I miss it, and apologize for my ignorance there, but not a lot of work has been done on the leaching of phosphorus in our soils, so to speak. So this was some work that I think was done in Eau Claire, where phosphorus leaching was positively related to the soil test. That means you have a higher P. Bray or Olsen or Melick or any of them, then you have more P losses, and that the losses is higher, obviously, in sandy soils, as one perceives, when the soil is saturated and when there's preferential flow, and that's the topic that we're particularly interested in for marsh fields. So, as I mentioned, much of our work is going to focus on marsh field. Many of the soils there are not well drained. We know that in fact 40% of our soils are not well drained. We should perhaps focus on that. We also know there's very dense concentrations of dairy farms in that area. We also know from the work of USGS, for example, that there is very high phosphorus in the streams in that part of the state. And some of the critical concentrations in soil water, in surface water, is very low in order to get this bloom of unwanted algae, for example, is only a tenth or hundredth of a milligram per kilogram of phosphorus is required, which is a very low concentration. If you think about it, the soil solution, often for plants, it can be 0.2 and 0.3 milligrams per kilogram. So this is worrisome. You need a little phosphorus to get a green lake, so to speak. Now, this is again, I think, the work from USGS, where they have the total phosphorus in milligrams per liter situated here for different parts of the state. Marshfield is in the north central hardwood forest. You can see if there's a larger percentage of agricultural land use, you have a higher percentage of phosphorus. All right, I will say a few things about the drainage, since 40% of our state is not well drained, and we should perhaps pay a bit more attention on it. What we'll do in these glossic alpha soils, so those are the alpha soils that have a glossic horizon in which the textural B horizon is broken down. It's very common in many parts of the state. And if that means that, for example, you have very big textural differentiation within that B horizon, you have perhaps an order of magnitude less clay or less silt in this part of the B horizon than in that part. And that's a complex process. We've studied it elsewhere, where you see there's a loss of clay, and because of that, you get a preferential flow in many of these soils. And that preferential flow is possibly, as we will try to understand, a way of leaching soils, a way of leaching the phosphorus. All right, here's Marchfield. That's our sampling plan. We have a Latin hypercube sampling design to study all that. I'll have only a few minutes left, so I'll run through this. These are the things that we'll develop, but I think the main thing is that we'll develop these digital phosphorus maps that essentially show, if you were to do any intervention, where is the phosphorus really high and where is the potential for the leaching on the runoff the largest. So we understand the runoff and the leaching quite well, but perhaps we haven't mapped it as well. So the other thing that we'll do is that we'll not do traditional analysis, wet chemistry so much, but most of our work will be done using mid-infrared spectroscopy. And that we'll use for almost all our soil analysis. It's a very fast way, it's reliable, it's quick, it reads much more than just the phosphorus, it reads lots of other things. It doesn't have direct absorption features, but we can predict the phosphorus quite well from the spectra. And there's lots of examples. I'll just give some examples here. The main number to look at, I think we're all a bit obsessed with R squares. I don't know why, but the R squares are quite high for many of our phosphorus measurements using the MIR. I'll just give other things. The phosphorus absorption index is also quite well related and quite well predictable with mid-infrared spectroscopy, and so is total phosphorus, for example. So phosphorus here too, these are just examples. At last, I think the notion here is if we can measure it, we can map it. And I think that's a thing that we should do perhaps on a large scale. Once we've figured it out for Marshfield, we might be able to do it for many of the other counties, or maybe for most of the less well-drained parts of the state. And we know the conditions that affect the phosphorus. We can assess it, we can identify it, we can map it, we can upscale it. And the other thing that we'll do, much like the weather folks have been doing for a long time, we'll assess the uncertainty. So it's not that we'll just say there's a very large, there is whatever, 75 milligrams of phosphorus here, but we'll also say how certain we are in many of these predictions and how certain we are that these hotspots are creating problems downstreams. And we have all the tools and hardware to do it. And with that, thank you very much.
We have time for a couple of questions before a 5-minute break. Andrew?
Hi, thank you. Maybe this is a question that you'll come to the answer to later on, but I was wondering if you had a sense of whether you think hotspots for P leaching will be the same places that are also hotspots for P loss through runoff, or if you think those might be different locations.
Yes, I think they might be different. So the leaching might be related to the glossic horizons, if you like. The runoff might be related to the topography, or the lack of infiltration, or the poorer drained versions of many of these soils. So that might not coincide with each other. I think the glossic horizons is generally better developed if the soil is a little bit less well drained. If it's really poorly drained, these glossic horizons don't develop that well. So I think the distinction between phosphorus accumulation in runoff and phosphorus leaching is a different one. But both create hotspots, we sense.
Thanks.
I have a related question, and that's, the idea of whether or not these phosphorus leaching hotspots could be nitrate leaching hotspots, and if there's a way to couple with the previous conversation in terms of monitoring activities.
Correct. I would say that is very likely. It's very likely. It's a different mechanism, though, I guess. And because the nitrogen leaching is not necessarily related to saturation, and you don't have that iron and aluminium sort of binding and the more difficult complex. As already shown in the previous slide, the nitrogen cycle is much more complex in that sense. I think the hotspots of phosphorus accumulation are also the hotspots of nitrogen denitrification, I would say. I think particularly if the drainage is poor, and there's lots of, there's a bit of literature there, I say, that is really pleased with that aspect of denitrification, because then you don't have the leaching. However, as we all know, that nitrous oxide is a bit more potent than nitrate in the water in terms of climate change.
We have time for one more question if there is one. Oh, okay.
When you talked about this technology, you talked about mapping it at a county level. Is this something that would be feasible at a farm level as part of a nutrient management plan? Every 10 years, maybe you map your hot spots or something, or is that going to be likely to be cost prohibitive?
No, I think it's a very good question. I think we can map it at any scale, but the accuracy will determine, or let's say the accuracy of mapping will determine the budget, if you like. So if you can say we're about 50% sure that that where the hotspots are of phosphorus saturation or phosphorus runoff, you might say as a policymaker or whatever, say that's not sufficient. We want to be 80 or 90% sure, and then we can say, well, we can do it, but obviously it involves more work and more sampling and more detailed approaches. I think it can all be done at any scale, at any cost. But the big secret is probably the uncertainty attached to it. If you're going to say we'll map the phosphorus hotspots in the poorly drained areas of Wisconsin, we also attach the uncertainty of it or the accuracy with which we map it. And if you're not happy with that uncertainty, understandable because it might be too high, then we say we need to go back to the work and to the field and sample. Good question.
Well, thank you so much, Alfred. We're going to have a 5-minute break, so we'll meet back here just about 11. And yeah, just feel free to use the restroom, get some water, and come back in 5 minutes. Thank you.
At the end. Also, there are going to be questions that you did say. Thank you. They know. Yeah. I kept looking at that. Different life activity. Yeah. I think we're all, yeah. So that was about 5. If you raise your hand like 5, but he didn't look at it. And they looked at it like 5. Yeah. I had a 5 on my kind of do something. Yeah. Right. We should still be there. This pretty good. Yeah. Hi, Susie. So, yeah. Well, I don't know if we have attention on it. Yeah. Never got it wasn't anymore. You guys are I should say.
Mic test. No.
Yeah. Well, yeah. I mean, the problem with it is you gotta kind of jack it up, make the unpack, right? It's not a lot of that. They've worked up their past. Done the dark. And you're writing. So CD. Writing on that. Yeah. I don't know. Just write it something. It's all just like flat. Yeah. Do the budget and then expand the job. Yeah. They want to see what they can do on effort first. Well, so yeah, for now. So we know what number we have to work with. So it's sketch basic sketch down. So I guess. Yeah.
There was originally more trials. Tyler was up there. He applied on.
Then the next thing is, yeah, so are we gonna build with, like, So I think that the number we- Send that in, match, and then the indirect. So anyway, so it's only probably like this carbon. I have the numbers. Like 600. Think about $1.5 million. If we go,
Yeah, no, you might be, so I think you're ready. I think most. I mean, I'm not even technology. If we can figure it out, it's much money. Then it makes sense.
You like the lights back on?
No, I love that. Yeah, whatever. I don't care.
Well, I honestly do. I hate breaking up good conversation, and I can only imagine the discussions about biochar and phosphorus happening in the. But we have a really exciting hour over the for this next session. Let me find my notes here correctly. So our next group of speakers for the hour will function as we're going to go back to back to back, and then we're going to save all the questions for a panel at the end. And so this session is apologies, titled Enhancing Dairy Farm Sustainability, Integrated Strategies for Manure, Land Management, and Soil Health. And so it's a collaboration of some of our newer faculty members in our college. The first speaker will be Gregg Sanford. He's currently a senior scientist in the Department of Plant and Agroecosystem Sciences at UW-Madison, and will begin as an assistant professor in the Department of Soil Science through the Dairy Innovation Hub position starting this fall. After that, we have Natasha Rayne. Dr. Rayne is an assistant professor in the Soil Science Department and an extension funded faculty working in the area of nutrient management and manure management. Previous to her position here at UW-Madison, she served as a faculty at UW River Falls. She also has had several projects funded through the Dairy Innovation Hub. And then the last speaker is Dr. Xia Zhu-Barker, who's an assistant professor also in the Department of Soil Science, also a Dairy Innovation Hub funded position, and also has a lot of research funded by the Dairy Innovation Hub. So collectively, we're very excited to have you all here, and why don't we start off with a round of applause for Dr. Sanford.
I'm loud without a microphone, so I'm a little bit nervous about this. We did tweak the title a little bit. You know, we're going to focus on soil health, nutrient management, and reduced greenhouse gases. And as Matt indicated, we have kind of 3 vignettes and then time for questions. And we're going to nest these vignettes. So we're going to start off at the cropping system level, talk about some of the research I'm working on, ecological intensification and its impact on soil carbon in particular. Then move into nutrient management. My colleague Natasha is going to talk. And then Xia is going to fill it out with some of the kind of novel manure technologies that she's working with. You know, some of the work that I've been working with now since, I guess, 2015-ish has to do with this idea of ecological intensification in agricultural systems. You know, this idea that can we bring ecological principles, niche complementarity, all the types of things we think about when we think about agroecosystems functioning at a larger landscape scale to impact some of the ecosystem services we're particularly interested in. And in my case, one of those is soil carbon. The research that I'm going to talk about today is being conducted at the Arlington Ag Research Station at a long-term experiment called the Wisconsin Integrated Cropping Systems Trial. This experiment was started by my PhD advisor, Josh Posner, back in 1990. It's a pretty unique study. When Josh built it, he built this study around the idea of cropping system enterprise type. So we've got 3 cash grain rotations without kind of a livestock component. We have 3 dairy forage rotations, pretty classical Wisconsin systems, and 3 native tallgrass systems, which would have been dominant ecosystems or biomes in the region prior to European settlement and cultivation of these prairies. From an agroecological standpoint or a biophysical standpoint, these kind of categories of cash grain, dairy forage, and native plants don't matter so much. What really matters is kind of these continuums of perenniality, diversity that we see in these systems and the impact those collectively have on our biophysical parameters. The ecological intensification work we do started with some studies in the mid 2010s, 2012, where we looked at 20-year, now these data that I'm showing you are 30-year trends in soil organic carbon dynamics. This is down to 60 centimeters, where we saw that all of our grain systems, whether or not they were organic or non-organic, had cover crops, didn't have cover crops, were no-till, not no-till, were losing carbon. Our dairy forage systems and our cool season pasture had been able to stabilize or maintain carbon over the course of this 30-year period. And it was really only our prairie systems that had been able to build carbon stocks. And that makes sense to some degree because these are the systems that originally built those prairies. So the question is, can we build this kind of perennial functionality that's able to stabilize carbon and potentially accrue carbon into some of our leakier systems from the standpoint of carbon? And so I'm going to talk about 2 phases. One of them has happened. The other one is going to happen. The first one is this kind of initial ecological intensification research, where we're looking to enhance ecosystem services, in particular soil carbon and soil health, while maintaining or improving yield and or maintaining and improving the economic kind of profitability of these systems. And the way we've gone about doing this, sometimes you hear these things talked about as soil health practices or regenerative agricultural practices. They fall into some large groupings of increasing the amount of cover in a system, whether it's through cover crops or polyculture, so spatial or temporal, reducing disturbance, and then really reintegrating livestock, which is kind of what dairy systems are about at a systems level. This was funded through a NIFA grant and ran 2019 to 2022, where we essentially took the systems at the Wisconsin Integrated Cropping Systems Trial, and we added cover, we reduced tillage, and added manure, again, all at the systems level. And then we have 2 kind of subset systems where we combine these, but maintain a fully grain system and combine them and maintain a fully forage system. WICS is 34 years old, so the ship turns really slow to make big changes, but we actually reinvented the systems here. We took the original experimental unit, maintained a control that would be consistent with those 34 years, applied our 6 interventions randomly in a randomized complete block design, and then maintained a control plot to kind of serve as covariate. And I just want to say that this first portion of the experiment ran for 3 years, which is a super short amount of time when we start talking about carbon change in these carbon-rich soils. And so kind of the way we attacked, whether or not these systems level reinventions or changes were going to potentially impact carbon was to look at some pretty sensitive soil health indicators. So what you're seeing here is particulate organic matter carbon in grams per square centimeter. This is our control, adding cover, reducing tillage, adding manure, and then our 2 combinations. And if you look, they look like not much has changed. These are population kind of densities. But statistically speaking, we are seeing shifts, small improvements when we add manure and begin to combine these practices. And I think what's most exciting about this is that when we look across the board, we did this to different systems, we did this to different phases of different systems, we see that there's no significant system effect. We are seeing a significant effect of this ecological intensification intervention, and there's no interaction. And so what that's telling us is that our specific interventions are moving the needle. It's not so much an interactive or system-specific effect. This is POM. We're also seeing these shifts in things like total microbial biomass, arbuscular mycorrhizal fungi, et cetera. So very promising. I will say that in these first 3 years and with this data, we've seen no reductions in yield. So that would be like a second kind of added benefit to this approach. But the real question is, great, we're seeing these improvements in soil health. But again, the question was, how do we get these annual systems to stabilize or begin to sequester carbon? And so that's where phase 2 comes in. This has been unofficially funded, but should be officially funded here in a couple days. Really to ask the question of what we're seeing in that phase 1, what it means for total carbon. And so we're taking a 3-tiered evaluation approach to build out on this. The first one, of course, is to go back 6 years in and ask the same questions we did 3 years in about the soil health parameters. That's kind of the way we monitor carbon, is by doing it over time. But then looking at other mechanistic approaches of what's happening in the system, and in particular, what the big levers are. What's going to give the most bang for the buck? Is it cover crops? Is it reducing tillage? Is it this livestock integration? And so here we're going to take an approach of C13 labeling, where we label both cover crop and manure inputs with deltas or with C13, and then we track the change of carbon 13 in particulate organic matter, mineral associated organic matter, and then some of the microbial profiles. And then follow that up with a complete greenhouse gas balance where we look at CO2, methane, and nitrous oxide, and wrap that up with a finalized economic analysis. And again, this was just, we just got news that this has been funded, this proposal, which should run until 2027 to kind of fully flesh out this study. So with that, just to tie up my portion here, theoretically speaking, from ecological, agroecological principles, ecological intensification should work. A lot of the soils in the Midwest were built by several hundreds, if not thousands of years of tallgrass prairie, and they are very carbon rich. And so we're working with a difficult medium to accrue or stabilize carbon in. We are seeing improvements in carbon inputs, carbon cycling, carbon use efficiency. There's a kind of array of studies that have come out of this long-term trial that add to this. So we're hopeful. Early results, again, no yield loss. We are seeing some improvements. The question is, where does that go? And that's the direction we're moving in. So I just want to say thank you to the team that did this first portion of research. And I think I'm out of time, and I'm going to hand it off to my colleague, Natasha.
Thank you, Greg. I apologize ahead of time for my voice. I had been battling a cold, so please hang with me. All right, so we've heard a lot about manure already. Well, why manure? We produce a lot of it, right? So nitrogen credits from manure. Two quick comments before we dive in. Nitrogen credits, what is that? What are they? Well, we're talking about nitrogen availability from manure. Okay, that's one thing. In my subtitle also, you might be curious because I ask, is there a right answer? You might be sitting there going, what is the question? Well, I'm glad you asked because the question here is, so what are the different strategies, methodologies that are used to calculate this, but also looking at, okay, what do we do next with all this knowledge? So what I'll be doing here in the next few minutes is diving into what we know and opportunities to move forward. All right, so it's no secret. A lot of manure is being applied to ag land all over the U.S., including here in Wisconsin. If you're looking at this, right, first of all, an interesting fact is that 80%, roughly 80% of the corn acreage in the U.S. receives manure. That's why we're here having this discussion. So one of the reasons why. But if you're like me, you're looking at this chart and what jumps at you is that poultry manure. So what we have here in this chart is all these animal types and all the manure or the manure nitrogen that is being applied, the nitrogen in manure that's being applied to land. And what jumps out at me is that poultry manure. Well, because we're thinking mass, we're thinking volume, and we expected to see higher numbers for the cattle manure. Am I right? Yes, kind of. So what this teaches us is that, yes, there is differences between manure types, right? In the amount of nitrogen that is, that is present in those manure types. So that's what the important lesson here is, that manure comes in different types, right? Manure is not created equal, and clearly the poultry manure there outdoes the rest in terms of its nitrogen content. All right, so if we dive even deeper, so staying with the idea that manure is not created equal, right? Even if we were to take one type of animal, so animal species, and just stick to dairy, you'll find that even under the different dairy types, right, the different manure, the forms of manure that are produced, there's different nitrogen content, phosphorus contents, and so on and so forth. So there already we have some variability, right? The solids are different from the semi-solids and liquids, and so on and so forth. All right, it would be wonderful if all this nitrogen was just available for us. Well, it's not, right? During handling, processing, storage, and land application, we lose some of this nitrogen, and that is what we want to dive into. So not all of this nitrogen is really available for plant uptake, plant use. See, the thing with nitrogen in manure is that we have inorganic nitrogen, right? Nitrogen that is directly available in the form of ammonium. However, the problem with ammonium is that it can be lost as ammonia. Then we have the organic portion of it, which needs to be mineralized before it becomes available, right? So it needs to be converted to ammonium and nitrate, plant available forms. So what we're left with is available nitrogen, which is the ammonium that is not lost, and available nitrogen that comes from that mineralized nitrogen, right? So this needs to be mineralized. Now, this takes time. This takes time. And it's exactly here where we have some challenges, because how do you predict this? Right? How do you predict this? All right, in an attempt to understand, and this was part of a larger study done at River Falls, we wanted to understand the mineralization of nitrogen over time. And this is a lot of manure, 30 tons, 60 tons of manure per acre. That's a lot. Now, we looked at that, and what we're learning from this graphic, we just not only manure, we have nitrogen applied as urea, and then urea in combination with manure. And what we're learning here is that it takes time. for that nitrogen in manure to break down. Because if you compare these two to, say, for example, just urea here, that nitrogen shooting up by V8, growth stage V8, you don't see that same thing happening with the 30 and the 60 tons. Are you still with me? All right. All right, in our current recommendations, and this is from our 82809, the nutrient application guidelines for the state, we have some estimates, and this is over years and years of studies, of course, where we say that, for example, with dairy liquid, 30, 40, or 50% of the nitrogen will be available as a function of time to incorporation. So the time that goes between your application and you actually incorporating the manure, right? You can lose much of that nitrogen in the form of ammonia. All right. So the longer you wait to incorporate it, the more you lose. That's a takeaway here. All right. So different studies have shown different values for nitrogen availability. This was a study that looked at 2 years, 3 locations here in Wisconsin, and first year plant availability ranged from 12 to 63%. I'll let that sink in for a moment. 12 to 60, that's quite variable, okay? That's quite variable. Other work, by the way, the technique or the method that was used here, we call it fertilizer equivalency. Well, let me just explain that for us real quick. In fertilizer equivalency, the method is really, they look at manure rates, nitrogen rates applied in manure. They look at fertilizer nitrogen rates, right? And the two basically that give you the same yield, in this case, whole plant nitrogen uptake, in this case, right? But people also look at yield. The two numbers that give you the exact same nutrient nitrogen uptake in this case, right? Those are the ones that they compare, right? So in our example here, the nitrogen availability would be calculated as 60 over 194 coming from the manure times 100. So we have a recovery, or a nitrogen availability rather, of 31%. Now in this study, first year availability ranged from 8 to 68%. In another attempt here, this was a study done near River Falls in Baldwin, Wisconsin. We looked at digestate, different manure types. We had different manure types, and we looked at nitrogen recovery. Now, nitrogen recovery is different from fertilizer equivalency. Here, you compare the nitrogen uptake relative to basically your control. That's why you don't see the control plotted here, right? Everything is compared to the control and then divided by your total nitrogen that you applied. And we found that for anaerobic digestate, a low rate of anaerobic digestate, we had a higher nitrogen recovery. But here also, this was the first year of study, we found a recovery that ranged 2 to 52%. 2 to 52%. What do we learn? Well, in our current recommendation, we say, well, if you're going to apply manure, you need to account for the nitrogen that is present in the manure. However, what we see and what I try to get across here is that there's a lot of variability, a lot. And that is oftentimes due to manure type, bedding, environment plays a big role, timing and method of application. And it's in particular this last part that my lab wants to focus on, looking at different timings of manure application and methods of application and how that affects nitrogen availability over time. But there's a lot of opportunity to refine our current estimates from manure. In accounting for weather, looking more at what that weather, the role of weather in these nitrogen credits. Nitrogen credits based on soil type, there's also an opportunity there. I talked about application methods. And then other products, anaerobic digestate, compost, my friend there in the back, biochar, right? We're wanting to look at, the incorporation of biochar. We started to do some work with Patrick Woolcock out of River Falls. But yeah, so that there's an opportunity there to look at the nitrogen credits coming from these byproducts. Come save me, Xia. It's your turn. Thank you.
Thank you. So as Natasha mentioned about like they have a lot like manure-based product, and we need to understand the nitrogen credits and at least the nitrogen cycling, right? After we use those kind of credits, those kind of products in the soil. So this come to my research, which is to evaluate like a process-based manure, like process dairy manure product, and how after we apply, those products into the soil and how that is going to impact our environmental footprint of the agroecosystems and also from the agronomic benefits wise. So here today, my talk, this is still ongoing project. And today I'm going to specifically focus on greenhouse gas emissions and in terms of nitrous oxide emissions here. All right, so we talk about a lot about dairy. So I would like to kind of put a snapshot here to talk about dairy sector, why we are here and what we are doing here. So first, if you look into the diet, right, in the American food and diet, and we have like 1/3 of our diet is from the dairy. Let me see here is from the dairy products. So those days, Americans eat more dairy than drink. This is because we eat more cheese and yogurt, those kind of stuff. And the dairy sector, if we look across all the commodities in the U.S., so dairy sectors rank number 4, and with a cash receipt like about over $51 billion in 2022, and it is about like 12% of the total here. And if we look at the resource use, that U.S. dairy is about like we use 5% of U.S. water and also 3.7% of the U.S. farmland. And if we look at the projection and all the history of U.S. dairy consumption, we can say the consumption per person is like increase. And also as the population is projected to increase in the future, and we can envision the demand of the dairy will increase a lot in the future. So there is where we are. And for the dairy cows in the U.S., and we can say they have many states that will produce dairy. And with Wisconsin, we rank number 4, just right below California in number of cows. But we are very proud of our cheese production. We are very big cheese production state. And so if Wisconsin is like we were a country, it would be ranked number 4 here. We are like 4 in terms of cheese production. So in the United States, about 26% of cheese, from Wisconsin. So this is like we are very proud of this. So while our industry is doing so well, and there are also some fact, and we would like to put here is like U.S. dairy also has a measurable impact on the global greenhouse gas inventory. So here is like you have about like 1% of the emissions is from the globally, and we have about 1% of the greenhouse gas emissions from U.S. agriculture. And the dairy, if you look into the specifically in the United States, we can say dairy farms contribute to about 22% of the U.S. agricultural greenhouse gas emissions. As most of us know already, U.S. dairy, we have the initiative which come from a U.S. dairy net zero. So the goal of this initiative, one of the goals is to become carbon neutral or better. In that, in other words, is like we want to reduce our greenhouse gas emissions and increase carbon sequestration in the whole dairy system. So for the farm wise, and if you look into greenhouse gas emissions specific for the farm, and then we will know it's about like about 55% of the farms from cow, like enteric methane emissions. And then they have about like 30% of the greenhouse gas is specifically come from the manure management and the land application of manure. So my work here is jumping into here is to specifically focus on this 30% to try to find a way like how can we reduce greenhouse gas emissions in this like among this like category. So to do this kind of work, so we come up with the idea of like, if we process this manure to separate solid from the liquid, would that help us to reduce the greenhouse gas, especially nitrous oxide emissions? And also, if we apply those kind of processed manure, is like how that is going to impact the nitrogen in corn, like silage corn systems. So here we tested 3 treatments here. First is liquid manure, which is business as usual. And the second one is a chemical separation. Basically, you use the coagulant to separate the manure solids from the liquid part. And the third one is a physical separation, which we don't add any chemical, but just use the screen to separate the solid from the liquid. And we applied those materials into the cornfield in Arlington. And also we used the fertilizer M15 to trace the fate of fertilizer nitrogen in these cropping systems as impacted by those different manure products. And also we could take a lot of gas measurements and to look at the greenhouse gas emissions. All right. Okay, so here comes to the results here. So we look at the nitrous oxide emissions. So here again is, as many of you already know, nitrous oxide is a potent greenhouse gas emissions. So that's why we look into the nitrous oxide specifically for this study. So we applied manure like in May, and then we continually measure nitrous oxide emissions here. So you can see after you applied manure, they have a big emissions peak after the manure application. And then we have the fertilizer applied right before the July, and we didn't see much emission over here. The main reason for that is because last year was too dry. And there is no precipitation. And after you apply it, of course, there's nothing happen over there. And then in the middle of towards the end of July, and we start to have rain, and you can see all those kind of huge peaks come up, and we have a big emissions of nitrous oxide. So those are kind of like falling into our expectation of the gas emissions. And then, because remember, we used the M15 fertilizer treatment, the M15 labeled fertilizer. So we were able to identify or separate the sources of nitrous oxide emissions. One is from fertilizer, and one is from the soil plus manure. So here is it's very surprised. We didn't find that much of the nitrous oxide emissions from fertilizer itself. So that means you can see this huge peaks. The difference between those 2 graphs are from the soil plus manure. So this is something like kind of fall out of our expectation. So here, we also look into the cumulative nitrous oxide emissions over the growing season last year. So you can see the control, which we didn't put any manure treatment over here. But it's like I want to mention here is we still have a business as usual in terms of the regarding the fertilization application. And this is a liquid one. This is a chemical separation, and this is physical separation. And then you can see we applied manure, and they have more nitrous oxide emissions than the control. And even like we have different treatments of manure, they still have more than the control, which it makes sense because we put more nitrogen, right, and carbon into the soil. Of course, they have more greenhouse gas emissions. But if we compare among those 3 treatments, and we found that if we process the manure, there is a potential help us to reduce the greenhouse gas emissions here. With the physical one is have a bigger promise on this. And also we look at the crop biomass and to understand what's the impact on the agronomic aspect. We found that the physical separation kind of increased the yield, the crop biomass compared to just liquid, and also compared to the control. And this is very draw our attention a lot for this treatment. And also we look into the soil in organic nitrogen concentration. So this is specifically for nitrate concentration. The main reason we didn't report ammonia data here is because we didn't find that much by the time we collected the samples. So this is before the manure application. Basically, it's kind of baseline of the soil. You can see most of nitrate is distributed on the surface, like 0 to 15 centimeter. As when you're going down further, and you have less nitrate over here. And then this one shows the post-harvest to see it's like how we are, where is nitrate? And we can see they still have a lot of nitrate on the surface. But if you compare to the before and the after harvest, we have even more nitrate accumulated on the soil surface here, which is like very interesting because on the control, look at this, we didn't put anything there, but we still have more nitrate compared to before the manure application. So that means during the season, they have a lot of nitrogen mineralization from the soil itself. So that's could be another information that when we're doing the nitrogen nutrient management, like how we can incorporate the soil mineralization into our nutrient recommendation. All right. And so the takeaway information for this ongoing project is first, if we do the separation, if we separate liquid and solid, and the manure has the potential to reduce greenhouse gas emissions, specifically nitrous oxide emissions compared to the standard business as usual, like liquid manure. And also during the growing season, surprisingly, we found more nitrous oxide emitted from the source of soil and manure than fertilizer. And the next step for this conclusion would be further, like if we can separate the nitrous oxide emission from the manure versus soil. That will be another very exciting piece. And also we found like more like nitrous oxide was emitted from the soil than fertilizer. So the solid manure can lead to a slight increase in biomass and compared to the standard liquid manure. So this is at the very end, I would like to thank my collaborators. And the first is my two graduate students, and they worked very hard towards this project. And they're still working in Arlington right now. That's why they're not here today. They're collecting the gas emissions and the soil samples right now. And also my other collaborators, Gregg and Aidan, thanks for their help to help me to jumpstart this project and provide other like in-field support. Of course, some like funding, funding sources, especially like Dairy Innovation Hub. And without their support, I guess I'm still sitting in front of my computer and scratching where I can do what I can do. With that, I would like to thank everybody. I think we can move to the next slide.
With that, I'd like to invite all the speakers up on the panel. Question in the back.
For the last study, when you show the effects of corn biomass, did you measure any parameters associated with nutrient composition or nutritive value?
The answer of that, no. Thanks for the question. The nutrient value of the biomass. Oh, excuse me. We want to clarify the question we got. I mean, I took the question in the right way. So your question were like, was like if we measure the nutrient value of the manure or crop? Yeah, the crop, no. You do?
Yes.
All right. I guess Gregg did, and which I didn't.
Yeah, there's kind of coupled studies here. Our lab is working on one of them, and Xia is working on the nitrogen cycling. But as part of the agronomic profile of the study, we do have nutrient composition of both the silage and the cover crops. I don't have those data on hand, but we do have them.
And in relation to the last study as well, so you looked at chemical separation and physical separation. It looked like you only looked at like the solid manure. So in terms of like the total picture, if you spread that liquid as well, how would it balance? Do you have an idea of how it would balance out in terms of compared to just business as usual?
Great question. Thank you so much for bringing that up. So yes, we only look at the solid part. The liquid part is like after we filter, if we do the separation, there's still, I can think of there still have a lot of nutrients in the liquid part. For the chemical separation, it depends on the coagulants, the type of coagulants you use, and the nutrients left in the liquid part could be very different, right? But for the separation one, could be very standard one. If we apply those kind of water into the soil, which based on my knowledge right now, those part they are liquid. Most often they will go through the different like the filtration and then to produce clean water. So that will another part will come out as solids or some like a fairly sludgy product out of this kind of water treatment process of that. So in that kind of term, I would not envision there will have a lot of greenhouse gas emissions by applying that part of the product into the soil, which we specifically focus on the soil part. I hope that will answer your question. And do my colleagues have other thought on that?
So this is for the second study. I guess I have two questions. The first one is, so it's the reason why poultry manure is more effective than like mammal manure because they have the different digestive systems, so the urates would be more concentrated. And then the second question would be, when you applied the dairy manure and you added urate, was it a urate concentrate, or how did you, what did you add for that?
Okay, so your first question pertained to the poultry manure. And what I was trying to show there on that first chart was just basically that there's differences in different manure types, right? And the poultry manure stands out to me simply because of its higher nitrogen content, right? Now, specifically where that nitrogen comes from, that I haven't dissected. Yeah. And your second question, sorry, I forgot that.
The second question was, when applying the dairy manure and you added a urate, was it a urate, right? Did you say?
No, I don't think so.
Urea fertilizer.
Oh, urea.
Was it what exactly was that?
Oh,
you
just
add?
urea prills,
Okay.
right? Yeah, urea 4600, 46% nitrogen. Yeah, 00. Thank you.
Thank you. Maybe a question for all three of you. So Dr. Zhu-Barker gave a nice overview of how much manure is being produced in the entire state. Do we know the carbon sequestration potential of that manure? Do we know how much carbon we can fix if all that manure was applied properly? That's the first question. The second question, maybe part of it is, we know that there's gaseous losses. We know that nitrous oxide is very potent. Does that offset the potential carbon sequestration if all the manure was applied correctly?
You ask hard questions.
I just would like to say from an agricultural standpoint that I think nitrous oxide and nitrogen management is the biggest lever that we have from a greenhouse gas standpoint. It's the easiest to manage from an application standpoint, potentially the easiest to develop efficiencies or improve cycling of, from an input standpoint. Once it's in the system, things get really complicated. But from an input standpoint, it's a pretty big lever we can manage to reduce the greenhouse gas impact of cropping systems. The carbon sequestration question, I think, is mostly a black box because we don't entirely understand what appropriate application of manure is, right? If most of our manure systems are dairy lagoons that generate methane and are losing carbon, does that mean we should go back to solid? Probably not. And all of those are going to have different kind of impacts once they're used in a system, whether they're incorporated, injected, surface applied, that type of thing. So I think that certainly it would be nice to have tightly integrated systems where forages or feeds are coming off, being fed to livestock, and those nutrients are going back to those same acres. But I don't know if that will happen.
Really quick about that carbon. So over time and long-term studies, right, Alfred, have shown that, you keep applying manure. What happens is that the carbon levels are maintained. You don't see a decrease and you don't see a sharp increase either over time. So, yeah, that's my best answer to that right now.
All right. First, I would like to thank Alfred to ask this hard and very good question. This question basically I asked like when I started my position 2 years ago to think about like how the manure management will impact the carbon sequestration in soil. With the discussion with my other colleagues like Matt Rurik in the past, basically, if you apply the liquid manure as business as usual, we didn't see any increase of the carbon in the soil. Majority is because they will be decomposed right away, and also have other kind of primary effect of using this manure application over there. So, and now coming to another question about you specifically, kind of ask is like if, just in the case, if the manure application can increase soil carbon, can that offset the other greenhouse gas emissions like nitrous oxide emissions? My answer to that one, I would say no. Because we look into the gas emission species, carbon does not behave in the same way as nitrous oxide. Even methane is not, because methane is about only 20 years, and carbon dioxide, if it's not from fossil source or from the reconcentrated carbon, that is not considered as greenhouse gas. So in other term, or in the simple way, is once nitrous oxide is emitted, it stays there forever, not forever, for 100 years. So this is like in the different terms of that. So if we want to increase soil carbon to offset the nitrous oxide emissions, I do not think that is going to be really